In this video, we will explore the airflow in cyclones and anticyclones. Let's begin by examining the systems on the surface weather map and find out what is the pattern of the pressure gradient force in them. Both cyclones and anticyclones have circular isobars. In an anticyclone, the pressure is highest at the center, gradually decreasing as you move outward. This creates a pressure gradient force that points from the center outwards. Now let's move to the cyclone. In a cyclone, the situation is reversed. The pressure is lowest at the center and it increases as you move outwards. So the pressure gradient force now points toward the center of the system. Now let's switch and examine the wind pattern in both anticyclone and cyclones on a surface weather map. We already know that the pressure gradient force initiates the movement by air driving it from high to low pressure. However, two additional forces influence the wind, the Coriolis force and the friction. These forces cause the air to be deflected, so it doesn't move directly from high to low pressure, but instead crosses the isobars at an angle. In the case of an anticyclone, the air moves outwards from the high pressure center and it is deflected to the right due to the Coriolis force, which results in a spiral pattern. The blue arrows on the map represent how air is deflected as it moves outwards. This deflection causes the airflow to spiral outwards in a clockwise direction in the northern hemisphere. In a low pressure system or cyclone, the air doesn't move straight towards the center. Instead, the wind also creates this spiral pattern of movement inwards. However, in this case, the rotation is counterclockwise in the northern hemisphere. These wind patterns in anticyclones and cyclones create distinct airflows. In an anticyclone, the air moves outwards from the system and is called diverging air. Conversely, in a cyclone, the air flows toward the center of the system where it accumulates. This inward flow is referred as converging air. Now let's find out how surface wind patterns create vertical airflow in both systems. Here we have a cross-section of an anticyclone. We have already seen that at the surface, air diverges outwards from the center. This outward movement creates a partial vacuum, which causes air from above to be drawn toward the surface. At upper levels, the air converges and supplies more air for this downward motion. As a result, we have sinking air from above, and this sinking air doesn't favor cloud formation. That's why typically in anticyclones, we have stable conditions, clear sky, and light winds. Now let's watch a simulation of the airflow in an anticyclone. Now let's examine vertical airflow created in a cyclone. At surface level in a cyclone, air converges toward the center and accumulates there. Since the air has no place to go, it begins to rise, and at upper levels diverges, making room for more air to ascend from below. This divergence at upper levels is crucial for the cyclone's development as it allows the system to intensify. The upward motion in a cyclone promotes cloud formation and precipitation. This is why cyclones are typically associated with unsettled weather, cloudy skies, and precipitation. Now let's watch the simulation of the airflow in the cyclone. We will explore the weather pattern created by cyclones in more details later in this course.